Standing waves and harmonics. This video is devoted to relating what we've learned about standing waves to harmonics, or how we make music on various instruments. So let's start with a practice problem. Suppose a wave is generated on a string that is tied down at one end, very similar to the FET simulation that you just completed. The string is 6 meters long. Draw the first 3 standing waves that can be created on the string, or what we call the first 3 harmonics. And if these waves are traveling at the speed of sound-ish, 343 meters per second, what is the wavelength for each of these harmonics? Practice drawing these into your notebook first, and then resume the video. Okay, so here we go. We're going to draw the first 3 standing waves that can be formed on this string. And I'm going to use my best artistic abilities here. So the first one can be formed when you have half a wavelength on the string. And so we can see here that the wavelength is going to be 2 times the length of the string. So the wavelength is going to be 2 times 6.0. So it's going to be 12 meters long. Second harmonic can be formed when I double the frequency or halve the wavelength. So I will draw 1 wavelength onto my screen, and I will realize that the wavelength is now the length of the string, and so my wavelength is going to be equal to 6.0 meters, half of the original. Now my last one, I'm going to actually have that wavelength again, or triple the first fundamental frequency. And what I'll have here is 1.5 wavelengths on that 6 meter string. That means that the wavelength is going to be 2/3 of the length of the string. So we'll have 2/3 times 6.0, which will turn into 12 divided by 3, or 4.0 meters in length. And so this is how we decide the wavelengths for each one of these first 3 harmonics, first 3 standing waves. But how do we figure out the frequencies? I made a mention that the frequencies are going to be doubled in each case. Let's see what that looks like in terms of sound. What we're going to do is we're going to play with the note A. And I'm starting with A1 at 55 hertz, but if I play it, you won't hear anything because 55 hertz is below the threshold of human hearing. However, if I double that to get A2, you probably can't hear a sound. I can barely hear it on my computer at home. That is pretty much at the threshold of human hearing. And then if I go to A3, this is the first time I'm able to hear the note A. We're going to call that the fundamental frequency because that's the first note A we're able to hear. So what I'm going to do now is I'm going to graph this. You will see that there are half, 1, 2 wavelengths in a time interval between 0 and 0.01. And cleaning this up, you'll see half, 1, 2. There's a reason why there's multiple peaks in here, and we're going to talk a little bit more about that next week. Now what I'm going to do is I am going to double that frequency again and see what happens. So I'm going to go to 440 hertz. And you'll see now that there's 1, 2, 3, 4, 5 peaks inside that same time interval. So this clearly shows that when I double the frequency, I have the wavelength. And each time I perform that, I actually get a new harmonic. So my fundamental frequency was 220, and then my second harmonic, my second frequency I can create from the fundamental frequency, had a frequency of 440 hertz. Now, if I was to triple this, I should get about 9.5 to 10 crests in that time interval, but that sound is a little bit too high pitched and a little bit too messy to get on the graph on my computer at home here. So hopefully you see what it means to double or make multiples of that fundamental frequency in order to create new harmonics. So how can we find the frequencies that go along with these standing waves? The first frequencies we're going to find are the first three harmonics for stringed instruments: guitars, pianos, bass guitars, violins, so on and so forth. So remember, to find the speed of a wave, you multiply the wavelength times the frequency. Or we can rearrange that equation to say that the frequency is equal to the speed of a wave divided by its wavelength. And remember that the speed of sound is a constant, and it's usually around 343 meters per second. So now we know we have this formula to find frequency, and we have these relationships between the lengths of the strings and the wavelength. So putting the two together, I should be able to come up with a formula to find the fundamental frequencies on a stringed instrument if I know the speed or the length of the string. So here we are, deriving a formula to find the first harmonic. We know for the first harmonic that the wave that is formed is 2 times the length of the string. So what I'm going to do is plug in this relationship in for wavelength, and I'll find that the frequency, the first fundamental frequency, is the velocity of the wave divided by 2 times the length of the string. To find the second frequency, I'm just going to double this whole thing. 2 times V divided by 2L. Well, those 2's cancel out, and I'll find my second harmonic to be the velocity, speed of sound, divided by the length of the string. And for the third one, all I have to do is triple it. I'll have 3 times V over 2L. And I'm going to be left with 3/2 times the velocity, speed of sound, divided by the length. And I could keep going to find more and more frequencies. Putting this all into one equation, though, it looks like this. The frequency of any harmonic on a stringed instrument for any particular harmonic number is the harmonic number times the velocity divided by 2 times the length of the string. And you can have n be any number on a stringed instrument, because on a stringed instrument you can form nodes on either end. I take a moment and write this formula down into your notebooks, and make sure you denote this as the fundamental frequency, or for any harmonic on a stringed instrument. So now what if we've got an instrument that's an open pipe, such as an organ, trumpet, saxophone, or flute? So the same thing applies here. If you notice, on a stringed instrument, the first harmonic's half a wavelength. Well, on an open pipe, it's also half a wavelength long as well. It's just reversed of the string instrument. Whereas a string has 2 nodes and an antinode, an open pipe is just the reverse of that. 2 antinodes and a node in the center. And that's because on open ends or closed ends, you can't form a node. On the second harmonic, you've got one full wavelength. And on an open pipe, you also have one full wavelength. It's just in half wavelength increments. Here's half a wavelength, and here's the other half. So it's still one wavelength long, just opposite of the stringed instrument. And for the third harmonic, you've got 1.5 wavelengths. And here you've got 3/4 plus 3/4 makes 1.5 wavelengths. So the exact same formula applies to an open pipe instrument as a string instrument. It's just that the waves inside those pipes are reversed. So what I'd like you to do is write down the exact same formulas that you got on the previous slide, but rename those formulas the harmonic series equation for an open pipe instrument. Now, what about closed pipe instruments? So closed pipe instruments are instruments such as clarinets, oboes, bassoons. These instruments will produce different standing waves because one end is open and one end is closed. So since you've got an open and closed end and you can't form a node at a closed end, you can only have quarter wavelength increments inside of your tube. So for instance, here on this closed end, there's no possible way for interference, destructive interference to happen. So you are always going to have the antinode appear on the closed end. On the open end, you can have destructive interference, so you can have a node. So the first fundamental frequency will have 1/4 wavelength, and then it'll go up in half wavelength increments after that. So the next one is half plus 1/4 to make 3/4 wavelength. The next one after that is going to be 1.25 wavelengths. So here's 1.25 wavelengths. And the formula to find any frequency for a closed pipe instrument looks like this, where you've got the frequency can be found with n, which is an odd number harmonic number, times the velocity, speed of sound, divided by 4 times the length of the closed pipe. Now remember, just like in the FET simulation, n in this particular case has to be an odd number because you can't form a node on a closed end of a pipe. That means you only have one end. One is an odd number, so the harmonics will go up in odd numbered increments. So n is 1, 3, 5, 7, so on and so forth. And it's divided by 4 times the length because remember, the first fundamental frequency is 1/4 wavelength long. Write this formula down into your notebooks and label this the formula for a harmonic series for a closed pipe. You are now prepared to do the following problems, page 427, 1 through 4, 435, 24 through 26, 34, and 35. Hope you enjoyed this video and have a good afternoon.